So, welcome, ladies and gentlemen. Yesterday we took a look at derivatives by the definition of a derivative, all right, which was basically finding the slope between 2 points on a curve such that the difference between those 2 points approached 0, the distance in the x-coordinate, right? And we were able to find those derivatives, and it was a function that represented the slope of a curve, another function, at any value of x. Today we're going to learn some, I guess, properties of derivatives or derivative rules. And this will be good. Derivative rules, rules. Here we go. So the first one is the constant rule, which says that if f of x equals c, some constant, then f prime of x is 0. And that's what we'd found as well doing our homework, right? We recognize that pattern taking place over time. All right, then we have the power rule, which says if f of x is equal to x to the n, then what do you think? Oh, that should not be an equal sign there. Then the derivative of f of x, or f prime of x,
n
times x to the n minus 1th power, right? So you'd multiply the, right? So we were able to do that. Then let's see, this is the constant, yeah, that missed the letter n there, constant multiple of a power rule.
Of course.
Where it kind of combines these two things-ish a little bit. And what if my original function was equal to, do they use c? Awesome, they do. C times x to the n, then what would the derivative be?
ncx to the n minus 1.
NCIS. Right, where you multiply that constant by n still. And I mean, this that technically agrees with what happened here. The coefficient there was 1, and n times 1. So I just want to point out that that is in agreement technically. And let's see, the last one is the sum and difference rule, which really gives us some ability to start breaking up some of these polynomials fast. Sum and difference, which says, what if f of x is equal to like g of x plus or minus h of x? Right, where I could break my function up into the sum or difference of other functions. All right, maybe even more than 2, right? So I'm considering my multiple terms of my continuous function. Then f prime of x, what do you think that will be equal to?
Prime of x plus or minus prime of x.
Yeah, right? I can basically find the derivative of each individual term separately and then just add them all together. Okay, so those are our derivative rules, which will make finding derivatives of at least polynomials el más fácil del mundo. I mean, really, this one I find is like the one that you really have to know, and then I think the other ones kind of follow suit. So let's see. So find f prime of x for the following. So let's say for part A, let's say f of x is equal to x to the 6th. So, f prime of x would be, well, it would be 6 times x to the 6 minus 1. You don't even have to write that down, probably. You could do it in your head. So f prime of x is just going to be 6x to the 5th, right? Makes sense, makes sense.
How can you type this first? It makes so
Well, because like shortcuts don't usually come out first. They
And
find
the
it by
second
definition.
derivative would be 30x.
Yep, second derivative would be 30x to the fourth. Exactly. What if f of x, what if I have some polynomial x squared minus 4x plus 10 or something to that effect?
2x minus 4.
2x minus 4, and then the derivative of 10 is 0 by the constant rule, right? It's constantly 0. Right, and notice that the derivative of a second degree function becomes a linear function. The derivative of a sixth degree function became a fifth degree function. Interesting stuff there, if I might say so myself. What if the original function was this one? 2x to the fourth minus 7x cubed plus 12x squared minus 8x minus 10. Whoa.
8x to the third minus 21x squared plus 24x minus 8.
Let's see, I don't like the way that plus sign came out. Plus 24x minus 8. So interesting stuff. Yeah, right? Exactly. That's what I've seen, those math joke shirts that say don't drink and derive.
The equation of an asymptote can't
Yep. Let's see. What if, let me graph us the original function. I just want to show you some more relationships between this one, which will have a lot more bends to it. 7x cubed plus 12x squared minus 8x minus 10. All right, let's see. Graph, grid form, rectangular. And let's see, does this one have any good bends? No, that's too bad. I was hoping it'd be like a crazy fourth degree function. Let me see, maybe I can change that. What if I make this minus sign? Well, there's ish. Okay.
Oh.
All right. So anyways, so here's our original function. Display line style. Come on. Well, here's my new original function. All right. Actually, I wonder if I could even exaggerate that a little bit more, making this a plus sign. There we go. Okay. I just want a couple critical points going on here. So if I want to find the derivative, I think actually even this might have a construct graph. I thought there was a defined derivative function. Bam. So that kind of automates it. Actually, it even used the f prime notation there. And if I graph this, that's interesting. Let me change the color. And notice what lines up oh so nicely. Not quite. The end behavior doesn't. But I mean, we'll notice that the end behavior of the purple graph, here the slope is all negative, and the orange graph is getting negative y values, indicating that that slope is the case. Right, this slope is getting more positive, and so positive values for that. And notice, right, third degree function, right, compared to the fourth degree function. What about the x-intercepts of the derivative? What do those coincide with?
The peaks and the highs and lows.
Right, those coincide with
The minimum and maximum.
those critical points. Right, so notice if I was to line this x-intercept right here. Actually, that's not a very dark color. Come on. Here we go. So this x-intercept lines up with local min. This x-intercept lines up with a local max. and this x-intercept lines up with another local min.
Absolutely.
Actually, absolute min in that case. So, so I just want to point out that relationship. Actually, let me simplify things perhaps even more. Will this...
Okay.
They won't let me. They actually won't let me do the derivative of that. Oh wait, here it is. Double second derivative, right? Now let's graph the second derivative. All right, so it's 1 degree less. Color, I'll make it. I don't know, maybe dark green or something. So what coincides with the x-intercepts of the second derivative? Okay, so the critical points of the first derivative, so there's a maximum value, and let's see, and there's a minimum value, right? But what do you think how does this second derivative, oh sorry, what did I just do? Yeah, okay, green one's the second derivative, my bad. How does the x-intercept of the second derivative correspond with the first equation, the original one?
It's the maximum value of the first derivative.
What's happening on the first derivative? Let me see. Let me choose a different color. What's happening right here and right here on the first derivative?
It's
Maximum
no, it's the slope is staying the same. Slope is about the same.
What do you
On
mean?
the points surrounding it, the slope is.
Well, yeah, I mean, but like even this, like it points surrounding it are going to be all
But
similar.
in the extended line, it's not curved. It's straight.
It turns out, what would you describe this section of curve compared to this section of curve?
middle.
This section of curve is kind of opening up, and this section of curve is kind of opening down. All right? So these are actually, this indicates a change in concavity. All right, where this is concave up and this is concave down. And actually, I heard there's an interesting point during a political debate. I don't remember what it was about or when it occurred. But I guess like they were basically saying like, well, the unemployment rates are still increasing, but the rate at which they're increasing is slowing down. And this guy ended up saying a quote saying that this was the first time a second derivative had ever been used to win a political argument. Because like, right, in this case, right, this graph is still going down, but at this point something changes where suddenly the rate at which it's going downhill has started to turn. So it's like a turning point, but it's still getting negative.
And then the x-intercept for your third derivative would be.
There'd be even fewer connections between those. But yeah, changing concavity. So there's all sorts of interesting relationships between first derivatives and second derivatives. And I think it's interesting to see those graphs side by side.
And then the third derivative, we would have an x-intercept about after 1.
Would it have? I don't know. I already switched out. What are you saying? Let me view it from here. The third derivative
The third derivative would have an x-intercept at about 1.
at about 1. Yeah, because the minimum point on the green graph is,
Also, there's a change in.
And there's a change in concavity of the orange graph, right? Concave down, concave up, right? So all sorts of interesting relationships, and that's how these things have been used to do a lot of optimization, right? That's why I like the video that we looked at, or winning a political argument. The video we looked at earlier, like even mentioned that calculus is used within economics, right? So like if you can see where something is trending, you can kind of predict what may be happening in the future for stuff like that. So all sorts of valuable stuff there. So what about antiderivatives? Antiderivatives.
Would that be derivative to negative in power?
Perhaps. You could come up, if you came up with calculus, you could have come up with your own notation for that. At this point, if f of x is a function, let's say f of x is 2x. All right, so you guys would know how to find the derivative of that. You'd say the slope of that is 2 at all times. But what about the antiderivative will actually be denoted with a capital F? All right? So antiderivatives, the notation is capital letters. All right? But I kind of like, well, if I use to the -1, that would be an inverse and not a derivative. But what do you think the antiderivative of this would have been? What? What was that?
Say x minus h.
Well, let's think about, we know our derivative rules. How would I have gotten a 2 here? What would it had to have been in terms of x? What would have given me a 2? It would have been something x squared, right? And is the derivative of x squared 2x? If I was going in this direction, the derivative of this antiderivative should take me here. Is the derivative of this?
Yeah.
Yeah, right? And that's exactly what we would tell Uncle Dan when he asked us, what's the derivative of x squared? You'd say, 2x, Uncle Dan. And then you'd go eat, like, Thanksgiving dinner or whatever. Right? That's what you'd do.
We would.
Yeah, exactly. Yep. So that ends up being the case. But I guess, like, this is my question. If we're trying to develop a pattern in the other direction, how would I go from the 2 to the 1? Divide by 2. Exactly.
Divide by the highest degree. Or
What if-
divide by the degree of x plus 1.
Yeah. What if I had, let's see.
Or 1 plus the degree of x.
What if I had this? 3x squared. Could we?
Would be a capital X?
So what would, this is a new function. I guess I could have called those g's if I wanted.
X to the third.
That would be x to the third. So an antiderivative in terms of degree has to be 1 higher, right? But then the coefficient part's a little bit weird. I think you'd agree. You divide by the degree plus 1. Perfect, right? So here the degree was 2. When I divided by 2 plus 1, or 3, I'd get 1 there. Well done, sir. Well done.
How did you say that?
Yeah, man. He
No,
knocked
I
that
said
out of the
that.
park. He
I
did?
said that like 2 minutes ago.
2 minutes ago. What?
Wait,
Yeah, sure thing, Gottfried Leibniz.
Yeah.
Yeah, like we believe that. He's been writing you letters for a long time telling you about this idea.
Yeah, okay.
He's going to defame you even after you're dead.
You get the British Royal Society.
Yes, exactly. Classic.
Big fan of your work.
So let's look at some rules for antiderivatives. Antiderivative rules. He figured it out independently.
Just after I did.
Sure.
Don't be
It was in the same year, so.
try to claim credit.
So let's consider the power rule for antiderivatives. Okay? So if f of x is x to the n, then cap f of x, which is not how that would be read, the antiderivative of f of x,
X over n plus 1 to the n plus 1. Or x to the n plus 1.
x to the n plus 1, the exponent is 1 higher, and I divide the coefficient by n plus 1. I'll just write that as 1 over n plus 1. And now technically,
We need a new variable. C over n plus 1. Bring B C.
you can have any constant added to that.
And it won't change. You can add like a billion.
Right, you could add a billion, it could have been -2, it could have been plus pi. Why would an antiderivative have any constant That's a
Because
possibility.
when you reverse it, that constant is the y-intercept, and we don't care about the y-intercept, because it doesn't affect the slope of the line.
Right. So if I was to take the derivative of this, the derivative of this constant would have been 0, right? So the antiderivative, I don't know what that shift, whether it could be up or down. I don't know what it would be.
So we can write any derivative.
Well, we'll just write it in terms of plus c, all
And
right?
it would be mathematically correct.
Yeah, because we don't know, all right?
Wouldn't it be
Because if I gave you the slope of a function, you could find the antiderivative, but you would never have known what the y-intercept was. Question, comment?
Wouldn't it be c times x to the n?
No, because that could have messed things up as well.
Wouldn't it be c over n plus 1?
Nope, because this is unrelated to the exponent of this term.
But before.
Because this would have been like plus 0, and then the plus 0 became the plus c.
But I mean, like before, when you were showing us like the different properties, like the constant property and then the power property, and then when you
Well-
combine them, you use c times x.
Well, we'll see. That's what this next one's going to be. This next one's going to relate to that.
Possible power rule.
So if f of x, the original function, was, they use k instead of, well, I guess it has to be a different one than that. So if the original function is k times x to the n, then what's the antiderivative of that going to be?
K over n plus 1 times x to the n plus 1.
K
Plus c.
over n plus 1 times x to the n plus 1, and then plus some constant. All right.
My fat would never drink until
Yeah, of course, of course. All right, and that's what we found up here, right? So with this 3, I divided by n plus 1, where n was my 2, right? 3 divided by 3 became 1. Okay, and then there's, of course, the sum and difference. Sum and diff rule, which says if f of x is equal to g of x, well, I guess I'll write it this way, plus h of x. I'm technically messing this up. All right, that's fine. This will do. Plus or minus that. Then cap f of x. What would that equal?
Cap g of x plus or minus cap h of x.
Cap g of x plus or minus cap h of x plus c.
Because when you, or the reverse of that would be finding the derivative, and when you have something that isn't to the power of x, it just disappears when you find the derivative.
Here, check this out. Here's my purple function. My purple function is the antiderivative of the orange function. If I change my y-intercept for that, say I make it to minus 20, notice that the orange function does not change ever. I could make it minus 200. And notice the orange function staying the same, because the orange function is only ever defined in terms of the slope of that. And the slope doesn't matter where it was, shifted up or down. It had everything to do with the steepness at its points. So that's why if I'm working backwards from a function to its antiderivative, this y value, or this constant, doesn't matter. It could have been anything. I mean, I could make it... What?
It only matters in the derivative.
Yes. So if this was plus 50, notice that the derivative is still the same, right? So it ends up just working out that y value, because the derivative was only representing the slope. I don't know what that y-intercept or that shift up or down would have been originally. So that's why we just say plus c. So plus some constant is what that ends up being. So those are the rules. And these ones are a little bit trickier, I agree. A little bit weirder with the n plus 1s, but but it makes sense. So let's do an example, or exemples. Find the antiderivative. Find cap f of x. Don't worry, we're done right here. It'll be good. It'll be good. Let's say f of x is equal to 3x to the 7th. So cap f of x. We'll write some more work with this one. I'll divide 3 by what?
8.
I'm going to write 7 plus 1 times x to the 7 plus 1. Just so that way in our notes you can see where these numbers came from. So 3/8 x plus 8. Oh, nope. Yeah. X to the 8th plus c, technically. Right? Because I have that constant that I don't know what it could have been. But it could have been any
In the book,
constant.
is it use plus c?
Yeah.
And everything?
Mhm.
That's the answer
And-
right there.
And that would be the antiderivative of that function. And to verify... What?
It's so much simpler than it sounds.
Yeah.
It's just reversing the derivative.
And notice, what if I took the derivative of this?
It would be 3x.
What is cap f prime of x as my check? Right? I'd multiply this by 8, and I'd get 3, and then I'd decrease that by 1, and notice, right? So I expect us to be really quick with derivatives. Antiderivatives take a little bit more time, right? But derivatives you should be super fast with once you, I mean, we've only seen it today, but once we get on a roll with things, derivatives you can be really rapido with. So let's do this one. How about, what if my original function was 4x squared minus 7x plus 5? So cap f of x. What am I going to divide 4 by?
3.
Yeah, 2 plus 1 or 3.
3x cubed minus
7 divided by
2.
1 plus 1, x to the 1 plus 1, plus 5 x to the 0 plus 1 if you want, dividing by 0 plus 1. I mean, yeah, it's just going to be 5 to the x,
Plus c.
and then plus c.
What did you get the 1 plus 1 plus 7?
Because the original exponent was 1 here. Right, so it's the n plus 1 is what you're dividing by in each of those cases. So let's simplify. So this is 4/3 x to the 3rd minus 7/2 x squared plus 5x plus c. And that would be my antiderivative. And one last quick one. We've got time. Homework is on the board, though, if you're interested. What if I have this? X times x squared plus 2.
Homework isn't very important.
Isn't it? No, it isn't. Oh, I have to fix that. It is online, though. I'll post it in a moment. Yeah, there's no product rule for antiderivative. You know what I'm saying. No product rule yet, anyway, for antiderivatives. So I would actually just say, let's multiply this out, and then just take the antiderivative of that. Right? So don't be deceived or tricked by that. It's really not that bad. Just multiply it out.
How are you going to remember everything we've done all year? Plus half.
Yeah, you'll be fine.
Like, after
So let's
the
see.
first thing everyone failed, now we're going to have to remember again?
Plus, and then 2 divided by 1 plus 1 times x to the 1 plus 1 plus c. So this is going to be 1/4 x to the 4th plus 1 x to the 2nd plus c. So it's not that bad. But yeah, but really the big idea is ends up being like recognizing the relationships between the derivative and the original function, and just kind of all the cool stuff that comes as a result of that. So calculus ends up being incredibly powerful stuff. And really, I mean, a lot of the math that we learn in high school independently is valuable, but a lot of our skills and manipulation and stuff end up being necessary to do calculus which is way more real-world applicable than, I would say, most of the stuff that we learn mathematically in high school, even though that does have its own independent benefit in the real world. But nonetheless. Well, anyways, thank you, Internet, for watching. That's 30 minutes